All right. Hope everyone feels nice and recovered. Good spring break in order to get yourself recharged a little bit. And then we are finally at the long-awaited, long-desired numbers and applications. All right, so you should be very appreciative of this after we've earned it with everything else, right? Along those lines, what's happening on Thursday? Quiz, all right, learning opportunity, all right, to prove how smart you are. And that finishes up chapter 6. So what we have remaining is chapter 7, 8, and 9. All right, these are all much smaller sections, and these are all heavily back to values and applications, interpretation. All right, so it's give and take. All right, we're kind of leaving the proofs, all right, as much as Trig has proofs. All right, and we are getting into applications. This means a lot more words and a lot more pulling info out. Now, the difference is that this is all much more connected, right? So we really feel this stuff. All right, and we'll talk about the calculator usage here in a minute. Okay, so, all right, we're actually going all the way back to right triangles just to refresh on the information that we have. With our basic right triangle, right? Our go-to picture in Trig. In case some things you didn't know, right? All the angles in a triangle, all right? Alpha plus beta plus gamma, they sum what? 180 degrees. So if, all right, we have one of our angles is 90 degrees, then the other two angles together will sum 90 degrees. All right, we have talked about this multiple times, just refreshing. And what we started with and what we will continue to use, all right, glorious Pythagorean theorem. As long as you have, and what we're going to start doing is we're going to extend this, and with less and less information, we can find the remaining pieces of information. Because basically, in any triangle, not just a right triangle, you have 3 angles and 3 sides. All right, so you have 3 angles and 3 sides. And our goal is ideally, if just given one piece of information, how much could we identify? All right, and we'll see that given a minimum number of pieces of information, we can find the rest of it. So, along those lines, if I have a right triangle, all right, and I'm given one of the angles, one of the sides, I can find the remaining pieces of information. So the easy part is the other angle. If that's 40 degrees, what's the other one? 40. 50. 40 plus 50 makes 90, right? And that's always going to be our math. All right, so I have both angles, so that part was easy. Now, in order to find the missing side, what do? Or sides. Do I have enough information to use Pythagorean theorem? Sorry, Brandon? No. No, right? Don't have enough to use that. So, is there something that relates angles and sides? Yeah, what is it? You don't remember? What's this class called? Trig. Trig, all right? And in Trig, what are the functions of trigonometry? Yeah, the trigonometric functions. That's what they are literally called. SOHCAHTOA, all right, and the reciprocals, right? Those are trigonometric functions. Those relate angles and sides. That is the whole concept of Trig. All right, maybe it is too late in the semester, right, to talk about this, right? It's basically a day 1. And I mean, we did basically talk about this day 1, right? In the very beginning of chapter 5, when we introduced those, right? That's what I said then, all right? The trigonometric functions, that's what they're called. They relate angles and sides. That's what we do, all right? And so, given one, how do I find the other?
Just angles?
I mean, specific trigonometric function. And at this point, given what we have, pick one. What's your favorite?
Sine.
Sine. And I like sine too. Why? Why do we all like sine?
It's the first one.
Because it's literally the first one in the SOHCAHTOA. I was like, and we all do that. All right. So yeah, let's start with sine. and it doesn't, and we could pick any of them, right? So let's see, if I'm using sine, all right, and I have that side. So opposite, in order to use that 2, that means that 2 needs to be the opposite. And the hypotenuse, okay, so let's go ahead and call it x and y. So that becomes 2 over x, and what angle do I need to use? Do I use the 40? No, can't use the 40, right? Because actually that's the adjacent. So actually I need to use the 50 degrees. And we could do it in reverse using the 40 degrees, right? If I was to use the 40 degrees, what trigonometric function would I have to use? Cosine, right? To find x still. Similarly, all right, and if I started out like this, let's do tangent of, and now let's switch it up. Let's do tangent of 40 degrees. Is what over what? In context.
Opposite over adjacent.
In context.
Oh.
You're absolutely correct.
1 over x.
Well, one more time.
Y over 2.
Wow, 2. All right. And so, okay, so then the calculator work, all right? And this is the best part, is that, so quick algebra here, multiply that over, divide that across, x equals 2 all over sine of 50 degrees. And this one, okay, good. So I did set this up. So this one becomes y equals 2 times tangent 40 degrees. Okay, so we have 1 divide, 1 multiply. And then this is just a matter of what's the most important thing when you're about to do trigonometric functions in your calculator? Mode, yes. All right, what mode are you in? Okay, so always check your mode, and oh look, I'm in radians because we've been doing radians for 9 weeks. Okay, so I got to go to mode and switch that to degrees. All right, and the quiz that's coming up, you want your mode in radians still. All right, but then from here on, primarily we are going to be in degrees, but we still do radians on occasion. Okay, so just keep track of that. All right, if you're like doing this problem and you're like, I know I'm doing this right and it's coming out wrong, it's your mode, 100%. All right, we all make that mistake. And then it's just a matter 2 divided by sine 50. Oh, look. X equals 2.61. All right, similarly, 2 times tan 40. 1.68. Okay, so putting our values in 2.61, 1.68. So once I have my values in, all right, and then here's the big thing. Triangles are logical equivalencies, okay? That's what a triangle is. Where's the biggest angle?
Right angle?
The 90.
The 90, okay? Where's the biggest side? Hypotenuse. And it's always going to be corresponding like that. Smallest angle, smallest side. Second, right? And it's only low, high, medium, right? So, all right, all your ratios need to match up. And that's basically what a triangle is. So it is we're back to the point of, I've never been a good plug back in and check my answer person. But what I've always been good at is logic check. And that's what I want to make sure you guys are. Because plug back in, it's just more math. I was like, I already did the math. I don't want to do it again. All right. Logic check your answer at the end. That's the important part. And I was like, that all makes good logical sense. So I could move on and feel okay. If I made a calculation mistake, I made a calculation mistake. But it all still made sense. All right. Okay. And because the actual, just as a note, along those lines, if you are a double check your calculation person, Pythagorean and make sure all the values work out, right? Okay, all right, so the application fun. And while I dislike numbers in most regards, what I do love, all right, is application. Because this is the concept. Once I'm past the setting up of the problem, it kind of becomes boring. But I was like, this is the fun part. All right, so a lighthouse stands 117 feet high on a hill, 245 feet high. So its beam of light is 362 feet above the sea level. The light is supposed to be seen on the horizon about 26 miles away. This is the concept of lighthouses, right? All right, so the passing ships have a guide. The radius of the Earth is 3,960 miles. Fun fact, that's a true statement. All right, on average, okay. The Earth, because of the thickness of the crust, varies throughout the Earth, but on average, all right, the radius of the Earth is about 4,000 miles. Find if the light can actually be seen 26 miles away. Okay, so once you actually start getting distances beyond, feet, all right, once you start getting miles, what important thing about the shape of the Earth comes into play? What is the shape of the Earth? Right. Everyone agrees on that? No flat earthers? Okay. All right. So, all right. The Earth is a circle. And so actually, when we start getting this kind of distance, we actually have to start incorporating the curvature of the Earth. So I have my lighthouse. And technically it's on a hill. So I'm just going to call this whole distance 362 feet. And the idea is that distance we're hoping is 26 feet, but really our point is we are measuring that distance. So I know, I guess maybe I should, just for emphasis. So we know that is 3960 miles. And this guy is 3960 miles. This then creates an angle, all right, because our whole goal is to measure that guy. And I could call that X or whatever. And, all right, basically then I can set up a triangle. Oh, and this actually does remind me, recall. All right, so back in chapter 5, part 1, all right, the very first thing we talked about is arc length. It was definitely what we covered something day 1. S equals R theta. How we measure arc length of a circle, all right, where theta is an angle, and this is the thing I was just talking about, measured in radians, all right, and R is the radius. So that's actually going to come back into play. But what we can do first, all right, is set up our triangle. Okay, and so I'm just converting this all to miles here. All right, so cosine adjacent. All right, and basically I'm creating a right triangle here over the hypotenuse, and this is the long side. And this is just, I wrote this out just so we would know, but what is 5,280? Feet in a mile. So I'm just converting this completely to miles. That's all this is. I just wanted to show the calculation. Okay, what this becomes, and since I'm actually going to need this in radians, I calculated this. And we actually get to use the inverse function on our calculator, which is just the second, right? Second cosine gives us cosine inverse. All right, and I'm keeping this in radians of 3960 divided by 3960 plus dot dot dot. This gives me 0.00588 rad. distance. And since we're being approximate now, because we're actually gonna end, like, our idea is to end up with some distance in miles. But as long as you're keeping your numbers approximately like as good as you can, 4 decimals, I basically consider a minimum, all right? And I mean, I'm just being approximate with how many I have here. All because I want to use the arc length to see, okay, what is this actual distance? And remember that S is arc length, right? And it will be in the same units measured that R had. The biggest thing here is that the trick I always see is this must be radians. And especially since we're gonna be in degrees so often, but when we start using these formulas and all those formulas in chapter 5, all right, a lot of those ones, we did quite a few applications in the beginning of chapter 5. Those are all coming back. Okay, so, all right, basically we identified the arc length, okay? Is this distance? So can the light be seen 26 miles away? Nope. Is it close? Yeah. I was like, they probably didn't measure. They're like, it's about 26 miles. All right, so, but that is the concept of basically how we do that. Okay, navigation. So navigation is a fun thing, and it's definitely something you've heard of, right? Northeast, north-south, not north-south, northeast, northwest, all right, etc. Bearing is a big thing in navigation, and how bearing is measured, all right? North, east, south, west. Bearing is actually measured off of the north-south pole. So if we have the north-south pole, and I say northeast 20 degrees, that means that that angle is 20 degrees. So it's not like how we typically measure our angles, which is off of the x-axis, right? Everything we've done is we start on the positive x-axis and go from there. Navigation actually measures off of there. And then we could just pick a bunch of these. Southwest, 70 degrees. All right, so southwest, that's this quadrant, and 70 is something like that. And that angle is 70. And similarly, I could do it for northwest and southeast. All right, but the idea is that everything is off of, all right, the north-south pole. Oh, actually, that doesn't remind me one more. South 30 degrees. And sometimes you see it written like this, which is the same thing. South 30 degrees east, which is actually even more descriptive, right? Because that means go south, then 30 degrees off of that, go east. So that is alternate notation, although we're much more familiar with this, but this is also fairly common notation. Okay, so whenever you see talking about bearing or navigation, that means change how you're doing your initial picture. Along those lines, all right, a Boeing 747, made this at the beginning of the semester, takes off from O'Hare Airport on a runway bearing 20 degrees northeast. All right, after flying for 1 mile, okay. So we have a bearing. So 20 degrees northeast. After flying for 1 mile, okay, so that means actually we were given this distance. The pilot of the aircraft turns 90 degrees and heads northwest. turns 90 degrees, which creates a right triangle. Oh, excellent. Okay, and then after flying the plane 2 miles in this direction, what bearing should the control tower use to locate the aircraft? Which means basically we are looking, not basically, exactly, we are looking for that angle. And basically we've created a triangle and I know some of the information. I can do this multiple ways, but and I could find that angle and I could find that side and then I could like put this all together. There is a fast way to really just do this in one step. So basically I have this angle, side and a side. What relates those three pieces of information?
Is it cosine?
I don't think it's cosine because cosine uses ka, right? It uses the hypotenuse and there's the hypotenuse. Now, FYI, I can go through a process where I can slowly find all the information. I could find it all. But since I only care about one thing, always want to be as efficient as we can. So what relates just those pieces? Tangent, right? I have an angle, okay? And then I have opposite and adjacent, or vice versa. All right, so that actually gives me what I'm looking for and uses the information. Now, be aware, that's the fastest way to do it. I could do Pythagorean first and find the missing side. And then I could do pick a trigonometric function. I could find that one over there. And then I could do angle, and minus 180 and find the missing side. So there are lots of ways to do this. I just want us to look at this and see if we can find the fastest way. So in this one, all right, I have tangent, and I call that question mark, but let's call that theta. So that's actually theta plus 20 degrees equals opposite over adjacent, which then gives me theta plus 20 degrees equals tan inverse of 2. All right, and I'm going to go back to mode, and make sure we are in degrees. Convert back to degrees, which gives me theta plus 20 degrees equals 63.43 degrees, and then minus 20. Theta equals 43.43. All right, so I found the angle. So I'm 43 plus degrees off of, all right, the north line. And then the only other thing I have to identify is bearing all the way, right? So what direction are we headed? Northwest. Northwest. So northwest, 43.43 degrees. Since we were doing bearing, all right? Not only do we want the angle, but I was like, I want where I am off the north-south line. All right. So just a matter, I mean, biggest thing, and it's been true for as long as we've been doing it, Trig is all about make that picture. Make that picture, make that picture, make that picture. Sometimes the picture is already given to us, so this is nice. State trooper is heading 30 feet away off a highway. 1 second after a truck passes, the angle for a particular segment of highway is measured. All right. If the angle measures 75 degrees, how fast is the truck traveling? And as always, express in miles per hour when we're dealing with vehicles or planes or anything that moves faster than a bicycle. So if we are told, all right, the angle is 75 degrees. And basically we're looking for X every time because I want to see what that distance is. Once again, what relates this angle, that side, and that side? Oh, look, it's tangent again. And tangent occurs often, all right, when actually in the real world, because the hypotenuse, by definition, it's across from the 90 degrees, which means it is the longest side, which is also the most annoying side to measure. So we like measuring the shorter sides. So we do tangent often. All right, and in this case, I have X all opposite over adjacent. And calculate away. That one's just a number. All right, now, here's the other big thing. Okay, what are the units of what I just found?
Degrees.
What is it?
Degrees.
Is it degrees? I don't think it's degrees, because I found a side. Is it what else?
Feet. Or
Is it feet? I don't know, we're guessing a lot of things. Why do you think it's feet?
because we it's the 30 feet from a height.
Because that one's in feet. If that one's in feet, that one is in feet. Okay, now, here's the weird thing about this one. So typically, a triangle represents distances. But this is 1 second after the truck passes, right? So truck at 0 seconds, truck at 1 second. So it's not just feet, but feet what? Per second. So that one is actually, because we're trying to find a rate of speed, right? We're looking for miles per hour. Okay, so identifying our units on this one, this is why I drew us a picture, and the more complicated the ones, I start us with a picture, you know, so we can, like, because this is the complicated part anyway, and I want everyone to see that. And it's all about just keep reading. Once you're there, then we can go 11196 feet per sec. And then 5280 feet per 1 mile. And 60 sec, 1 minute. 60 minute, 1 hour. Then dimensional analysis away, right? That's all we're doing here. And calculate away. And the whole point of dimensional analysis, right? I'm quite sure we've talked about it. Feet. The units have to be on opposite sides of the fraction so they cancel. Sec, min. So what I'm left with is miles in the numerator, hours in the denominator. I was like, I know that seems like a simple thing, but it is a constant problem, all right? Making sure our units are correct is one of the biggest things we do now that we're back to application. And similarly, all right, if the angle measures 70 degrees, how fast is the truck traveling? And that's basically the same thing. Tangent of 70 degrees equals, it's the same setup, x all over 30, which gives us x equals 82.42 feet per second. And the conversion is the same as well, which gives us x equals 56.20 miles per hour. The point of this one is then to identify the relationship. All right, so the calculation is exactly the same at 70 versus 75, but otherwise all the same. Notice the difference. All right, 70 degrees, all right, is the distance the truck traveled, right? So that's 70 degrees per second is the angular momentum, right, that we talked about. That's the rate the angle is changing. Notice that the linear distance traveled then is much, much slower. All right, 5 degrees more in a second resulted in 20 miles per hour faster on a linear distance, even though the angular distance was actually very small. And that is basically always going to be a relationship that you could change this, all right, a lot faster than this distance. And so just kind of fun. Okay, one more, let's see. If the speed limit is 55 miles per hour and a speeding ticket is issued for exceeding the speed limit by 5 miles per hour or more, for what angles was the trooper positioned? So once again, that means 55, 5 over that is 60. We need to go back the other way now. Okay, so I got the 88 feet per second. So we can do the same thing. And since it's just 1 second, that means that our value that we were previously calling x is the 88, which is the opposite over the hypotenuse. And now we are finding this angle theta. We're trying to find that angle. And then I can solve that. Which gives us a value of 71.18 degrees. Now, the nice thing is I can verify that with the previous calculations I did. 70 degrees got me 56 miles per hour. 75 degrees got me 76 miles per hour. 71 degrees is in between 70 and 75. All right, almost like we chose those numbers on purpose. And then, so then the important thing, right? We were trying to tickets for people going 5 miles per hour or more over 55. So 60 was actually our minimum. So that means it's 71.18 degrees or more. And really 71.18 or more is all you need, but that concept, right? It was like something we learned basically when we first start doing math. If it starts in a sentence, ideally do your best to end in a sentence, but at minimum, make sure you have your units on there. All right. Good stuff, huh? Like applications are fun. Not as much fun as establishing identities, but still good stuff. All right, along those lines. So expanding upon, all right, so that was all right triangle trig. Expanding upon that, we don't need right triangles in order to identify missing sides and missing angles. We just need a triangle with some amount of information. So a general oblique triangle. And we typically label them A, B, C. And our angles we do in Greek letters, alpha, beta, gamma. So we have 3 sides and 3 angles, all right? We know those 3 angles sum 180 degrees. Those 3 sides could be any distance or any value, depending upon if it's a distance or a speed or something. But with the law of sines, we can actually extend this and solve, all right, with some amount of information, missing information. There are 4 cases. If you know one side and 2 angles, these are known as angle side angle or side angle angle. And those triangles basically with the information, what's known. All right, so it's always about what you know on a triangle, is how a triangle is labeled. Now geez Louise. The actual name of a triangle is not nearly as important as being able to use the information and find the missing stuff. So I almost always forget, like, besides angle side angle, which is actually the only one that I can ever remember. And that just means, all right, I have an angle, alpha, I have a side in between those, C, and then I have another angle, beta. So that's my known information, and everything else is missing. So basically I have question mark, question mark, question mark. And with 3 pieces of information, you can find the other 3. And that's what the law of sines does for us. Without this being a right triangle, right? Because a right triangle actually gives us 3 pieces of information. And so you're, quote, presented 2, but you actually know 3. And then side angle angle. So side, A, angle. So if that's alpha, beta, that's gamma. And then that one's alpha. And it doesn't actually matter which one you call A, B, C, all right? As long as you're consistent with, and a lot of people use uppercase for the side, lowercase, all right? If you really hate the Greek letters, although like this is good stuff, all right? But you can capital A, lowercase a, capital B, lowercase b, capital C, lowercase c, all right? Doesn't matter. 2 sides and the angle opposite one of them is side angle. So A, B, and then alpha. Side angle side, and you kind of see the pattern here, right? A, B, gamma between them, and side. This is actually the most interesting one. A, B, C. With all the sides, you could find all the angles inside. Notice what we didn't get, angle, right? Because it's impossible. Knowing all the angles tells you literally nothing about the side. You could be talking in millimeters or millions of miles, right? So just be aware, everyone's like, oh, what about angle? It's impossible. Triangle is, you need some information on the outside in order to be able to solve the rest. Okay, so those are the 4 cases. Those then correspond to 2 different laws, the law of sines and the law of cosines. And I do believe these are on your cheat sheet somewhere, hopefully. Okay. But this is a very purist cheat sheet is what that means. All right, these are the 2 most common applications, all right, of trigonometry once you get past right triangles. So the law of sines is just the ratio test that we talked about in the beginning. Sine of the angle corresponds over that side. And all this is a ratio. And basically any combination of sine of the angle over its side to one of the other ones, all right? We'll talk about sometimes like the mismatch of how they line up, but this concept, all right, is just the concept of ratios. And so it is a very, very intuitive, all right, formula. And we'll talk about law of cosines in a bit. So if I have side angle, angle, triangle, right, and I have the following information presented. So alpha, so 40 degrees, 60 degrees. And so A always corresponds opposite alpha, which means that side is over here. And with that information, I could find the remaining stuff and always do the easiest things first. All right. So what's the easiest thing to find? It takes almost no calculation. The other angle. And that other angle is 80 degrees. Once you have that, then you can start lining up. So sine of 40 degrees all over 4. All right, and this is what the law of sines says. So sine of 40, and then pick the other angle. Sine, and it doesn't really matter, I can do them in any order. Sine of 80 degrees all over and ABC, just to keep our notation the same. And then I can solve that one down for C. And similarly, sine of 40 degrees all over 4 equals sine of 60 degrees all over B. And I can solve that one down. And so I can use these ratios . And I can plug in the missing information into my triangle. Now, here's the big thing. The law of sines, there is kind of a weird thing, and it usually occurs like if you only have the middle. Something about if you only have the middle and you start with the large or something, your ratio ends up messed up. Now, this is the thing I always want you to check at the end, okay? Largest angle, largest side, smallest angle, smallest side, middle. Is all that right? Yeah. Yes. If you, and it'll just happen, I forget exactly the situation it occurs in, but you'll see that like if you accidentally, you have a choice between two of them and you pick the wrong one, your ratios kind of get messed up. It means pick the other one. You had a 50-50 shot, you guessed wrong. All right. And so just be aware of that, which is why I always do this at the end. All right. Because it is the fastest and easiest way to make sure, okay, my ratio is matched up. Because it's a triangle. All those ratios, and that's what the law of sines says, all those ratios are correspondingly correct. All right. Similarly, side angle. And so this one I need to actually start with the law of sines. Sine of 35 degrees all over 6. And I only have one option here. Sine of all over 8. There is no other, I have no other option of where to start. And then we can solve that down. And then once I have that, fill in your missing value. Using the sum of all the angles makes 180. And one last time, law of sines. Once I have everything filled in, and again, this level of calculation, right? Everyone's okay with the calculation occurring, right? It's just sine and sine inverse. I mean, that is basically the sum total on adding. All right, and then do all the ratios look good? Yep. And that's literally the check every time. I was like, that check, you'll be surprised how often it saves you. All right, A, B, C, and gamma 50. All right, so law of sines, sine of 50 degrees all over 1 equals sine of alpha all over 2. I want to show more of this calculation. Okay, so cross multiply, right? It's basic solve. Sine alpha equals 2 sine 50 degrees. When I actually calculate that, I get sine alpha of 1.53. Then when you do sine inverse here, what do you get? What'd you get?
Domain error.
What is it?
Domain error.
Error, domain error. Okay, recall. And it says domain error, but it's actually range error. All right. What's the minimum and maximum of the sine function? What is it?
Negative.
Yeah, -1 to 1. Okay, I thought I heard, I couldn't hear who was saying it. Right, by definition. The sine function ranges from -1 to 1. All right, and I showed this calculation slower because typically, I mean, I'm just busting this in my calculator until the same thing I get to the end with you guys and I'm like, whoa, it said error. All right, so I wanted to show this slower. So ideally, we would have seen this right here. All right, if you're actually writing this out. Because I know that this is bad news and this isn't going to work. Because this is already a value over 1. And what this actually means, all right, max value. Okay, so just further emphasizing, the max value of sine cannot be over 1, which means that I know this didn't work. AKA, this is not a triangle. Those angles actually don't work, so it's actually more something like that. All right. It actually, you can't just plug in any number you want, all right, and be like, oh, let's just make up numbers. Okay. A triangle catches basically itself, and it knows that the angles and the sides, all right, the ratios have to work out. Also, I was like, let's see. So 130 degrees is left. Okay. Which means that this has to be a bigger side. Okay, so this has to, let's call this
70.
yeah, 70, so what's left, 60? So then that side, like, there doesn't look like the ratios are gonna work. All right, so it'd have to be much more closer in ratio, because they're all gonna be around, I mean, 60, 70, something like that, right? 60, 70. So is that the biggest side? But I don't know if the ratios work out. And basically, that's what this is telling us. So it's kind of a fun fact there. All right, to measure the height of a mountain, a surveyor takes two sightings of the peak at a distance of 900 meters apart on a direct line to the mountain. The first observation, okay, wait, let's start drawing pictures. All right, so a surveyor takes two sightings at a peak 900 distance, 900 meters apart. First observation results in an elevation. Okay, so here's our mountain. And this one is 47 degrees. He then moves back 900 meters and takes a second observation. Okay, so basically we have triangle within a triangle here. This one is 35 degrees. And we are told this distance is 900 meters. Resulting in an angle of 35 degrees if the transit is 2 meters high. Okay, so the transit, we talked about this a while back. So it's like a little thing, got to stand. Basically, we're saying that whatever number we have at the end, we need to add 2 meters to it. The transit is 2 meters high. What is the height of the mountain? So with this information, and ideally, all right, so we actually do have the height of the mountain and the ground being level is the idea. So actually we have a right triangle, and then we have information on the outside as well, creating a second triangle, and all within I mean, we have 3 triangles here, but 2 main ones that we're going to focus on. Okay, so just like with everything, let's just start putting information together. And without a doubt, the easiest thing to put together, all right, is this angle right here. So what's that angle right there?
43.
43. What else is super easy to identify?
Angle, second. Triangle.
Which one? That one?
Yeah.
You think that one's easy to
Oh,
identify?
no.
There is one more that's easy to identify. You have to remember one other fact.
Doesn't that get equal 180?
Supplemental angles, right? We're always doing complementary angles, all right? We don't talk about supplementary angles nearly as much. So that plus whatever that is equals 180. And what number, whatever that is, 180 minus 47. 133. Now, do I know that guy?
Yep.
Yeah, because now I have 35 plus 133 minus 180, and that number is 12. Okay, so, all right, putting all that information together, then we can narrow it down. But basic concept of triangles, all right, and again, supplementary angles, we definitely don't talk about as much, but you be aware, right? I mean, that's the sum total of it. There it is. On a line, if you have 2 angles, they sum 180. Okay, then, okay, so we got all the angles, which is definitely, if you can always fill that in, fill that in. Then what can we do?
For the not the right triangle, you could do side angle.
Right, so law of sines, yes. And you're even better than I am already, because I never freaking remember those side angles. Besides side, like I can't remember them. So yes, law of sines though. I have that angle and that side, and then pick one. So I have sine of 12 degrees divided by 900 equals, okay, so is there one that's gonna, yes. So actually, I think I want to use that one because that's more helpful to me. Because eventually I need to get to this. All right, so I could do that one, but I really need that side more than the other side. So sine of 35 degrees all over, let's start labeling. Let's see, let's call this one y. All over y. And then we can solve that down. That gives us that. Then now I have a side on my triangle that really matters with the mountain on it. And I don't need to use law of sines. I could just use normal trigonometric functions because I have a right triangle again. And what relates the my and let's call it 47 degrees? What trigonometric function? Sine, our favorite one. Sine of 47 degrees equals opposite m all over y, which actually I have a number for, 2482.88, which gives me m equals 1815.86. And then one last little note. So actually, m equals 1815.86 plus 2. Since our transit, all those measurements were from 2 meters up. And basically, that's the concept, all right? Make your angles, start limiting it down, fill in everything you can, and then law of sines gets you there, and then, I mean, we have a right triangle, so that was important. I was like, if we didn't know that was a right angle, let's see. I know it's impossible because, okay, well, we could find this and then find this overall. Yeah, we might be able to do it. It'd be a lot harder, I feel like. And see, we wouldn't have known that was 43. So that'd be an unknown. That'd be an unknown. Yeah, we might be able to. But that's the idea. I was like, with lots of unknown stuff, you can start filling in the gaps. And so there is fun stuff here. Okay, law of cosines. The law of cosines, and be aware, there are 3 formulas here. They are all the same formula, just with rotating angles and sides. There's only one of these formulas I have memorized, and it's the same one that you should memorize or have written down, and then the rest you can adjust. If I cover that part up, does that look familiar? Pythagorean theorem is actually a special case of the law of cosines, all right? Because again, we are now at the stage where we have, we don't need a right triangle. When you have a right angle, cosine of 90 degrees, that is cosine of pi over 2, what value is that? 0. Oh, so look, that becomes 0. I know, we're back to the Pythagorean theorem. With any other angle, all right, then we actually have to calculate it. And all the law of cosines is this is basically angle side angle. Or side angle side angle side. So I have the side, the angle between them, and the side. And it's just those pieces being multiplied. And that's all law of cosine is. So we talked about the 4 cases. Those first 2 cases, these first 2 cases, these use law of sines. All right? These can always be solved with law of sines. These second 2 cases, you need to start with law of cosines, then use law of sines. But basically, we only have 2 laws. There are literally only 2 laws when it comes to finding missing pieces of triangles. And either you use law of sines or law of cosines, and then just solve it down. All right, so A is 2, B is 3, and 60 degrees between them. Now I always start with law of sines because even though law of cosines is not hard to remember, law of sines is super easy to remember. So when I do law of sines here, right, sine of 60 degrees all over the missing side there is C equals sine of alpha all over 2. What's my problem here?
You have two unknowns.
I have two unknowns in one equation, okay? That's bad news because I have two unknowns and I don't have two equations, right? Three unknowns, three equations, etc. So this is why the law of cosines is much better. So the law of cosines does the same thing, all right? But notice that I only need one angle in order to do it. I still need an angle and at least two sides in order to do this. And so this one, same thing. So c squared equals 2 squared plus 3 squared. Once I plug everything in, notice I only have one unknown, which is much, much better. One unknown, all right? And then it's just a matter of calculating away and square rooting. And C becomes calculate away, and I can find that. Once I have that, all right, then we convert over to the law of sines. So I have all the information now to actually go back to the equation that I had started up there. Sine of 60 degrees all over 2.65 equals sine of alpha all over 2. Then I can find alpha and find my missing side. And then 180 minus the other ones gives me beta. And we have our values and then double check large to large, small to small, mid to mid. All right, and our fourth case, side, side, side. So this one is fun actually when we find areas as well. We'll talk about that in a minute. A, B, C. I definitely can't use law of sines because in order to use law of sines, I need at least one angle, which means law of cosines is the only place to start here. Okay, so And so with just the sides, what this allows us to do is find a single angle. And that is very, very helpful. Once I have that, and then I have to, again, in order to find the rest, I need to use, if you're ever using law of cosines, you will use law of sines. And then we can find alpha. And similarly, beta. And looks like all my ratios are good. All right, it's pretty straightforward, right? One other, all right, big thing about triangles is area. Probably the first thing you learned about triangles actually is the area of a triangle. 1/2 base times height. Without a doubt, like the most common area formula you know, maybe besides this area of a circle. And we don't count area of rectangle, way too boring. So what's also nice is that the side angle side triangles that we were using with Pythagorean, we can do that to calculate area as well. And we did something similar to this when we were doing in our section 5, we were calculating the area of a like piece of a sector of a circle. And so that's basically the same concept. This is a triangle, and if you know side angle side, and two sides and the angle between them, you can calculate the formula. And these are actually very, very common. And again, the only one I ever remember is AB because this is just like basically the law of cosines. All right, AB and this one sine of the angle between them. And those other three formulas are the same thing. It's just changing the angle. You can have them all written down, but it's all side angle side. Two sides and the angle between them, which is why it doesn't matter which two sides you have, as long as you have the angle between them. Along those lines, so I want to find the area of a triangle, A, B, and gamma. And this is literally the definition. Of area of side angle side triangles. And there were no units, there's no context attached here, but just to recall, or just to make sure everyone's aware, these are areas we have now transitioned to. All right, we're not finding distances anymore. All right, so I just attached units squared, whatever that is. So that's a pretty common equation. The other one, and this is one that actually, I mean, we talk about this like in geometry. So it's probably been a while since you've seen this, but knowing just the sides of a triangle, you use what's known as Heron's formula. And again, this is an oblique triangle. So this is not a right angle. If I have a triangle, side 4, 5, and 7. So just knowing the sides, I can calculate the area of this triangle using Heron's formula. The basic equation of a triangle, right? 1/2 base times height. Notice I don't have the height here, and I can't find it easily, okay? Drawing a line down here, right, doesn't bisect this triangle. That's the big misconception, all right? Because this side is very possibly longer. And that's the thing that I see everyone, oh, I'll just draw the side, then I have, this is 3.5, and that's 3.5, and then I have a right triangle. It doesn't work like that, okay? Which is why I wanted to draw this triangle with this side much longer, okay? Which is why Huron's formula is so commonly used. And it is a very straightforward calculation. We calculate this value S, which is an intermediary, in order to calculate the other values. What do we got? 9, 16, 8. And then Huron's formula may look complicated, but it is actually very, very intuitive. It is just the intermediary term and then each side subtracted off of it. And as with everything, make sure you're double checking your calculation. None of those numbers end up negative, because if they end up negative, what happens? Yeah, square root of a negative becomes imaginary. Can you have imaginary areas? So besides just making sure your calculations are okay, this is actually very, very straightforward. All right. We have one more page to go. We'll pick that up and finish the rest and keep doing this lecture 1 week from today, all right? Because you guys are busy on Thursday.